All right, let's go ahead and get started. We've got lots to do today. So last class we started talking about arc length, right? And I actually was able to show that the circumference of a circle is 2 pi r, right? That's kind of where we finished up. But just going back to kind of reassess things, the idea here is that if we have a curve, let's say that this is some function of x, and we start this thing out at x equals a and end it at x equals b, that we can go out to some value of x, go up, and then take this like infinitesimal little piece of the graph, right? Kind of zoom in on it so that we've got this little arc like this. And then what we do is we approximate the length of that little arc with the straight line that is somehow related to the derivative. And the way I set it up is I drew a right triangle. I called this dx, I called this dy, and then to find, did I call it little l? I think I called it little l. I said, you know, little l squared must be dx squared plus dy squared. And then we solve for little l, and we got this thing right here. So this is all from last class. And then what I said is if we want to add all these up to get the entire length of the curve, we have to use an integral. And I said, but the problem is that this doesn't have like a little dx sitting out here, right? So then I did this very kind of clever little thing, and it's not my clever. I'm not claiming it to say that I'm clever. Someone else came up with it. And that's just factoring out a dx squared, all right? I could have factored out a dy squared though, right? Y dx squared. What would happen if I pull out dy squared instead? I would have gotten, let's see, we pull out a dy squared, and then here, because there's not a dy, I have to divide by dy squared, right? So that would become dx over dy, that squared. And then this one, when I pull out dy squared, I get a plus 1, right? See the difference? And now the dy squared, the fact that I'm taking the square root, that can pop out of this as a dy, can't it? And so I get this formula that's a little different than the last one. It would have a dy here at the end, and inside would be this piece, right? So I'm going to write that backwards. Like that, okay? So this would represent the length from here to here, and then if I want to add them up, I do an integral, right? So I've just provided you with a formula sheet, and I want you to take a look at the two formulas we now have for arc length. The first formula is the one from last class. If you have some function of x, right, then we can pull out that dx, and then what would be left in here would have been dy over dx squared. And dy over dx would be the derivative of that function with respect to x, right? Squared and then plus 1, and we figure that out. However, if we pull the dy squared out instead, then we're going to have this, and it'll be with respect to y, which means that we need to be looking at our limits of integration being y values instead of x values, right? And also importantly here, the derivative of x with respect to y would mean that we would have to rewrite this curve as a function of y. So it would have to be like x equals some function of y. And then we would differentiate that with respect to y. So it's like everything kind of switched places. Okay? So we're going to do a couple of examples of this. But there's one more little thing on the bottom here that is boxed right here. And it says that, look, these two expressions, this one right here and this one right here, came from exactly the same picture. It came off that right triangle, right? One of them I pulled out dx squared, the other one dy squared. But they represent the hypotenuse, right? Here, I need to include the whole thing. With the dx pulled out and then here with the dy pulled out. They both represent the little l, don't they? So what we call that is we call it ds. And s stands for arc length. Don't ask me, okay? All right, so the S stands for arc length. So really what we could do is we could summarize this, that if you wanted to find the length of a curve, what you need to do is integrate ds, right? That's what you need to do. You need to integrate one of these. Now, your limits of integration are going to depend on which one you use. If you use this one, your limits of integration will be your values of x. If you integrate this one, it's going to be the values of y. Make sense? Okay, so this is a very general kind of formula, but that right there, from here on out, you should look at that as being the arc length. Okay, ds is the arc length formula, which is this or that. Okay, and then we'll do surface area after we do a couple of examples, because I've got to convince you that that formula is true. All right, so I'm going to do a couple of examples right out of the book. Now, the reason why I have to do examples out of the book is because, as you'll see, it's not easy, in general, it's not easy to integrate or to find arc lengths, because the integrand, this piece right here, or this piece, can be very complicated and be something that we can't handle. So the author of the book has to create problems that can be done, and so I can't just make them up out of my head and make sure that they're going to work. So I'm going to use some problems out of here that I did not assign for homework, and that way we'll have a couple of examples to go off of. I guess I can't erase that. Okay, here we go. First one is this one. We have y equals 1/4 x squared minus 1/2 natural log x, and this is on the interval x is between 1 and 2. And I want to find the length of this. All right, so we have some curve, and we want to find out how long this curve is. All right. So I'm gonna graph it just so we can get a visual. We don't need to graph it, but I'm going to. If my computer just didn't update earlier, what the heck? Okay, here we go. Desmos. And we've got 1/4 x squared minus 1/2 natural log x. There we go. And we're looking between where? 1 and 2? Let me zoom in on this a little bit. So what we're doing is we're trying to find the length of this curve from here to here, that piece right there. That's what we're trying to do, okay? So we need to establish a few things. With the two formulas that we have, which of those do you think would be better for this problem? The dx one, right? And the dx one because this is a function of x already, right? So I want to use this formula. I want to use the fact that the length is going to be equal to the integral from a to b of the square root of 1 plus the derivative of f with respect to x, that derivative squared dx, all right? So we're going to need to find the derivative, and then we're going to need to square it, and then we're going to need to add 1, then see if we can integrate that. So let me do that over here. Well, we never called this f, right? I'll just come over here. I'm going to call that f of x, all right? All right, so f prime of x is, so what's the derivative of that? 1/2 x, and then 1/2 minus 1/2 times 1 over x, because the derivative of natural log is 1 over x. So I'm going to write it as 1 over 2x. Is that okay? All right. So this is our derivative. No questions on that, right? What do I need to do with that? Square it, right? Ooh. Okay. So if I need to square this, I mean, there's several ways we can do it. We could FOIL it, couldn't we? If we could do this times itself in parentheses, you don't want to do it that way? I don't care. I mean, let's see, 1/2 x minus 1 over 2x times itself 1/2 x minus 1 over 2x again. So here to here, what do we get? 1/4 x squared. Okay, now the middle term, we get this and this, so that's going to be how do we say it? Minus 1 over 4x. Is that okay? Minus 1 over 4x. And then what about this middle one here? No, and hold on, the x's canceled, didn't they? Oops, minus 1/4. This x and that x canceled. For some reason I wasn't looking at that. Agree? Okay, what about the next one? Same sort of thing, right? When you do here to here, this x and that x cancel, you just get the 1/2 and 1/2. So minus 1/4. And then the last multiplication, this times this. So plus, right, because they're both negative. And then you just multiply across. So 1 times 1 is 1, and then 2x times 2x, 4x squared. And I think if we combine like terms here, or get our constants together, that's minus 1/2, right? Minus 1/4 is minus 2/4, so that's minus 1/2, and plus 1 over 4x squared. All right, there's my derivative squared, right? Okay, so I think I'm ready to go into my formula here, or not go into the formula. Actually, I'm not ready to go to the formula. What I'm going to do is now figure out, I'm still doing scratch work here. I want to figure out what 1 plus the derivative squared would be. So it's like I'm trying to figure out all of this before I actually plug it into the integral, all right? So what would that plus 1 be? So if I add 1 to this, all it's going to do is turn this into a positive 1/2, right? So I'll get 1/4 x squared plus 1/2, and then plus 1 over 4x squared. Now I'm supposed to integrate that, right? Are there any questions on what happened here? Just added 1 to this, so that, yeah? Okay. So I'm supposed to take the square root of that, right? And integrate it, and I think we're going to have trouble if we do that, mostly because of that, right? That's kind of messy. Like you could integrate these term by term, couldn't you? But it's under a root, so you can't. Now, if it were a quadratic, like if this wasn't here and it were some sort of quadratic, then we could maybe complete the square, do something like that. But here's kind of what we're going to do. Let's get a common denominator between these fractions. So remember, this is really like x squared over 4 plus 1 over 2 plus 1 over 4x squared, right? So what's a common denominator? 4x squared. So this one, I need to introduce an x squared on top and bottom, right? That's going to make that an x to the 4th on top. On this one, what do I need to introduce on the top and the bottom? 2x squared. So I'm going to have a plus 2x squared. And then on this one, do I need to introduce anything? No, so just plus 1. All over my common denominator, which is 4x squared. Now, do you see why I would want to do that? If I put these together, I'm going to need the square root, right? So when I take the square root of a single fraction, I can do the root on the top and bottom separately, can't I? And I think that'll be a little easier to work with. There's one other thing that you need to see here. There's something about that numerator that's pretty nice. You can factor it. How? This is almost like a quadratic, isn't it? Back in college algebra, we call that a quadratic type. It's actually x squared plus 1 squared. So if you were to multiply this out, you would get this. Now, do you remember I said that we have to make these problems very nice so that they'll work? This worked like this because they made the problem so it would work. Like this needed to happen. If we couldn't do this, we'd be pretty jammed up on this problem. We wouldn't be able to complete it, okay? But they made it nice for us, so that's where we are, right? That's 1 plus the derivative squared. Now, let's go into the integral. So our integral, this right here, is going to be the integral from where to where? 1 to 2. That's given to us, right? 1 to 2. And then we're integrating the square root of x squared plus 1, that quantity squared, over 4x squared dx. Did you see me this weekend? I saw you this weekend. You were on the phone, so I didn't bother you.
Really?
Yeah.
Where was it?
You were outside of some place over there near Stoneworks right here off 1604. There's like a gaming place over there, and
Oh, I was coming back from Puhat.
well, I don't know where you were, but you were outside on the phone in the little walkway. You were just out there in front of the building talking on the phone.
Yeah.
I was with my wife. Yeah.
Oh, you could have said home.
Yeah, you were on the phone. You sounded busy. You were yelling. They were yelling. I could hear. No, I'm just kidding. Okay, so what happens here? I mean, this is nice, right? The square root on top kills that off, so you just get just x squared plus 1 right on top. And on the bottom, 2x dx. And then this, I mean, this couldn't be any better, right? Just split it into two different ones, like x squared over that, this over that. Okay, we may as well take it all the way, right? We come this far. So now we have integral 1 to 2. If I do x squared over this, I'm going to get an x on top, right? And a 2 on the bottom. So I'm going to write that as 1/2 x. And then if I do 1 over this, I'm going to look at that as being 1 over 2 x to the negative 1 dx. And I'm just setting it up like that so I can integrate. Y'all know what I'm doing, right? Yeah. I keep on saying right, like, yes? Okay. Okay, now antiderivative, right? So antiderivative of that is going to be 1/2 x squared, but I already have a 1/2, so 1/4 x squared. And then this one oh, should I have done that? Maybe I shouldn't have done that. Maybe I should have left it as 1 over x, because I'm integrating it, right? So it's natural log. Yeah. So 1/2 natural log x. Yeah, let me take that back. This right here is 1 over x. And then I should put absolute value around the x, but look at where my x's are going from, 1 to 2, right? So my x's are going to be positive, so I don't have to worry about the absolute value. And then I plug in 1, I plug in 2. So if we plug 2 in here, what happens? We get 4, that's a 1, right? So you get 1, and then we get plus half of natural log of 2. And if I plug in 1, I get 1/4, and I get natural log of 1 is 0. So we're going to have nice things happen here, right? Nice numbers, and we're just going to get an answer. We'll be done. I'll put it here. So 1 plus 1/2 natural log of 2. That's what we get when we plug in 2, minus 1/4 plus 0, because natural log of 1 is 0. So I think my final result here is 3/4 plus natural log of the square root of 2. Bless you. What just happened? What happened? What? What happened? Yeah, 1 minus 1/4 is 3/4, right? And then this, I pushed the 1/2 up using properties of logs and made that 2 to the 1/2, which is the square root of 2. So just make sure you see where all that came from. We good? That's how long that curve is. 3/4 plus natural log of 2. Okay, let's try something else. How about x equals y to the 4th over 8 plus 1 over 4 y squared. And we're going to do this where y is between 1 and 2. I wonder if Desmos will do this. I've never tried this on Desmos to try and graph something as a function of y instead of x.
Yeah, you just need to put
X equals? Okay, so that's what I figured I would have to do. Y to the fourth over 8 plus 1 over 4y squared.
Yes.
And we're graphing it between y equals 1 and 2. So let me zoom out here. Pretty interesting looking curve, right? So I'm trying to find the length of this between y equals 1 and 2. So that means you're looking at the y-axis. Y equals 1. Up here it looks like 2. So we're trying to find the length of that curve right there. Okay? So we'll want to use the other formula, right? We're going to want to use the other formula because that will definitely work better for us. We're going to be doing that the length is the integral from c to d of the square root of 1 plus, now this time I call that g of y, right? So it's going to be g prime of y, that squared dy. All right, so this right here is our g of y, since it's solved for x. Derivative, right? Derivative time, square it, add 1 to it. Let's see what happens. So what is g prime of y? Go ahead. Please raise your hand. Don't be yelling over each other like that. It's very rude. What do you got? 1/2 x, 1/2 y cubed, right? 1/2 y cubed plus 1 over 2y. Is it plus or minus? Remember, this is really, what is this really? This is 1/4 y to the negative 2, isn't it?
Yeah.
That's what that really is. So if I take the derivative, negative 2 comes out. So this will become negative 1/2 y to the negative 3 because you're subtracting 1 like this. Yeah? And then I'm supposed to square this, yeah? Okay, now I'm going to do this one a little different, okay? On the last one we just foiled it, didn't we? I'm going to just show you we could have done it a different way. I'm not sure this is going to be any easier, but let me first rewrite it. Do you agree that this is 1/2 y cubed minus 1 over y cubed? So I can pull a 1/2 out of both of those? Okay, I'm going to get a common denominator now between these two. So I would need, this is really like y cubed over 1. So I need y cubed top and bottom here. So this is really 1/2 and then y to the 6th. That would be that on top because I did y cubed top and bottom. Then minus, do I need to do anything here? No, right? Nothing here, so minus 1 over the common denominator y cubed. Now I have not squared this, right? I have not squared this. All I've done is I'm just rewriting it. And now I'm going to square it, all right? So g prime of y squared, since this is multiplication, I can square that, 1/4. And then when I square this fraction, I can square the top and bottom separately. So the bottom will become y to the 6th, and the top, if I square that, will become y to the 6th minus 2y, no, not y to the 6th, y to the 12th, minus 2y to the 6th plus 1. Could you do that, right? I keep on doing that. I ask you and then I tell you, I affirm the response without letting you say anything. All right, so if you FOIL that out, right, you get this. Okay. Is that all right? Okay, so now that's g prime of y squared. Now I need to add 1 to that. So let's see what would happen if I take 1 plus g prime of y squared. So if I do that, I'm going to have 1 plus, watch the way I rewrite this, y to the 12th minus 2y to the 6th plus 1 over 4y to the 6th. So all I did was just slid that 4 down here with the y to the 6th. And I did that because if I'm going to add 1 to this, I'm going to get a common denominator right here on this one. I'm going to rewrite 1 as what? 4y to the 6th over 4y to the 6th. So when I put those together, I'm going to have 4y to the 6th plus y to the 12th minus 2y to the 6th plus 1 over 4y to the 6th. And now I do have some like terms, right? This one and this one. So I have 4 of those, and I take away 2 of them. It's going to leave me with 2 of them. So I have y to the 12th plus 2y to the 6th plus 1 over 4y to the 6th. I'm going to have to take the square root of that, right? And again, notice when I take the square root on the top, it's like a perfect square trinomial, except that it's to the 12th. So that will factor, and that definitely I can take the square root of that. So same story is going to happen on this problem. Very similar. It's just that we're doing stuff with y's instead of x's. All right, so let's do the integral. Any questions? Where are we going from here? 1 to 2, right? Square root of, let's go ahead and factor this now. What is that? That's really y to the 6th plus 1 squared, and then over 4y to the 6th dy. I think one more step and we're there. Root on top and bottom. So we're going to go integral 1 to 2. When I root that, I just get y to the 6th plus 1. And when I root this, I get 2y to the 3rd dy. And then I can split it into 2 again, can't I? And then I'm just going to say from here you could do the rest, right? So both those problems actually worked out very similar to one another, right? Yeah. Okay. I think we can move on. We're going to get a little more practice with this as we move on to the next topic. Did you all celebrate Halloween this past weekend or what? No? I'm trying to figure out when are people celebrating Halloween? Is it the weekend before or after? Because it's on a Wednesday, so it's kind of weird.
Like before, and then other people are doing
Yeah.
it on the day of.
I don't think you're allowed to do it after, right?
Yeah, see, you can't do it after.
Can't do it after, right? Yeah. Yeah, I agree. I agree.
Like, you don't want to see people dressing up after Halloween. Like, it's just weird.
Yeah. Okay, we're going to move on.
Unless you're
Quick recap. Quick recap. Here's where we are. We go back to this very basic picture. There's a lot of things we can do with the function if you define it on some interval AB. We can find the area underneath this, right? We can wrap it around the x-axis, find the volume. We can wrap it around the y-axis, find the volume. Different axes, different lines of rotation. We also now can find the length of that curve, right? Okay, so now what we're going to do is talk about surface area. So let's go back to the idea of wrapping this around the x-axis right now. If we wrap this around the x-axis, we're going to get some shape that's going to look something like that. Agreed? I mean, good enough? That's wrapped around the x-axis. Now we know how to find the volume of that, don't we? That would be like if we wanted the volume, it would be integral. Well, we need a pi, right? So integral a to b, and it would be just the function squared. That's it. That would be our volume. But instead, what if we ask ourselves, what is the surface area of this object? So surface area is a different measurement, isn't it? Volume is the amount of stuff inside of something. That's a three-dimensional measurement. You need like a length, width, and height to talk about volume. Surface area is like flat sheet of paper again, right? Yeah. And you're trying to figure out how much space is taken up. So one way we could think about surface area is if we had this shape right here and we had to paint it, right? We would need to know how much paint to use, so we would need the area, the surface area of the object. So here's how we're going to go about it. And what I do is going to hopefully look very familiar to you. We're going to pick some arbitrary point x, we're going to go up, and this time we're going to take, just like we did with arc length, we're going to take this little infinitesimal little piece of it, okay? Just this little arc, this little piece right here. And we're going to wrap just that around the x-axis. All right, just that little red thing around the x-axis. Now that little red thing has a little arc to it, doesn't it? Yeah. Okay, so when I wrap that around the x-axis, I'm going to draw it over here. I've got this thing that's going to look something like this. Like a rubber band, if you wish, right? So it's not a washer, okay, because we're not doing a rectangle revolved, right? We're just doing that red thing revolved. So we have a rubber band instead of a washer or a disc. With me? So we want to know what the area of that rubber band is. So I'm going to come in here and I'm going to use my little scissors. I'm going to cut this rubber band and I'm going to lay it out. Okay, this is kind of like what we did with the shells. When I lay this rubber band out, this rubber band does not have thickness to it, all right? Right, when I lay it out, it's like, you know, you cut something, lay it out flat. We're talking about the area, right? So there's no thickness to this. Let's see if we can't figure out what that is. Like, what's that area? So, pardon?
Something like that.
Something with dx? Yeah. Okay, so I agree with that. I think this is this dx. Okay, yeah, you're on the right track. This looks like a rectangle, doesn't it? Yeah. But it's not quite a rectangle. Because this piece right here, right there, right, when we wrapped it and we cut it open, this is going to have a little bit of an arc to it. A little bit, it's curved now, right? Because that came from this piece being wrapped around. So let's say we cut it right there and open it up. That little arc would be over here, wouldn't it? Yeah. And in back here, it would be like this. So that when we paste them together, they would match up with one another. So this thickness is not dx this time. What do you think it is? It's ds. It's ds, right? Didn't I say just a second ago that little infinitesimal thing that we said was lowercase l was one of two things, but both of them could be called ds? They're the arc length of that little infinitesimal. That's how thick this is. The thickness of this is ds, not dx. Now dx would be if we were to drop this straight down as a rectangle. That's dx, but this has, do y'all see? I'm trying to exaggerate it now. See, that has a little bit of an arc to it. So this is ds. That's the height of our little rectangle. Now, how long is our rectangle? It's related to the function's value, right? Because when we rotate around the x-axis, this right here is the radius, isn't it? And that's the functions. So that's the radius, though. When we cut it open, we're not looking at a radius anymore, right? So when I look at this rubber band, right, here's the rubber band, just this edge here. And when I cut it and open it and lay it out, that length from here to here is what we're talking about. And that's not the function's value, it's the circumference of the circle. And circumference is 2 pi r, right, where r is the radius. So this is actually 2 pi times, what's r? The function, right? F of x. Does that make sense? So what's the area of this little sliver? This times this, right? This times this. And then what we need to do is add them all up. So we bring in the integral. Make sense? So let me show you those other formulas. They're in front of you. Anybody need those formulas if you came in late? I handed them out. How about formulas from last time? Formulas from last time, last class? Okay, so now look at this. Look at our surface area formula. This is going to look, well, you know what? I should have put this thing up here first. Okay, so if we wanted to know what the area was, right, we would have to do an integral. It would go from A to B because we're still going to be moving across here, getting those little arcs and then doing a bunch of rubber bands, right? And so I'm still going from A to B, but my formula is this times this, right? And I can get a 2 pi to come out because it's a constant. And then I have the function, right? F of x. But then times ds. Now what's ds? Well, it's one of two things, isn't it? It's one of two things. So I'm going to just put that up there for right now. But I want you to understand that that formula right there could mean one of two things. It's going to be either 2 pi integral from A to B of f of x. Now I'm going to call f of x y instead, okay? Is that all right? Because y is usually f of x. So y, and then square root of 1 plus something squared dx, right? So if I'm going to say that y is f of x, and this is supposed, if I'm doing it with respect to x, this should be f prime of x, right? Which would be y prime. Y prime squared. Do y'all see that? Or I could do 2 pi integral from c to d of what? Y still? Square root of 1 plus, not y prime, x prime. X prime squared with respect to y. So basically what I'm saying is this. If you want to wrap a curve around the x-axis and find the surface area, you get to choose which of these to use. See, and you know, I should take this off. Let's take A and B off of that. Did I take it off on the formula sheet? Hold on. On A to B. Yeah, you know what? Scratch that A to B up. I'll erase it once I get up here. But the idea is this. You have 2 pi and then the function itself and then ds, but ds can be one of two things. One of them is with respect to x, the other one's with respect to y. If you use the one with respect to x, then this out here is just going to be y. If you do the one with respect to y, right, then this is going to change to x prime, which is the derivative of the g function if you solve for x. It gets a little confusing. I understand that gets.
Would it be x instead of y on
Where?
Outside of the.
with respect to y?
It would not. That's why it's a little confusing. What did I? Oh, no, but that other one is if I rotate around the y-axis. That second formula? Is that what you're referring to? Yeah, see, I'm going around the x-axis right now. Okay, so see on my notes I have 2 boxes. Each of those boxes has 2 different versions. So this box is the first box I put up there, right? And I said take off the A and the B. Okay? So this one right here, it's either going to be y with this or it's going to be y with this. And the problem, when we do the problems, you'll see which one to use, all right? And then after we do a couple of examples, then we'll wrap this thing around the y-axis instead of the x-axis. All right? So let's do a couple of these. I'm going to do 2. That way you can see one of each of those methods. So those 2 boxes are actually 4 different formulas. All right? Okay, let's do this one. We're going to take y equals the square root of 1 plus e to the x. And we're going to be looking at this on x is less than or equal, or x is greater than or equal to 0, sorry, and less than or equal to 1. And what we're going to do is find surface area. I'm going to put SA for surface area if rotated about the x-axis. And while I remember this, I want to go back to those notes and take off that A and B that I was right here. This B and that A need to come off. Y'all see that on that first box? Take off the A and B, because if I put A and B, that means I have to go with respect to x. But this ds can either be with respect to x or y, depending on the problem itself. All right. So, pardon, what? Huh?
Oh, sorry.
Yep.
Just when you brought up the rubber band, do you know about that? I don't know if it's a riddle or some sort of a problem-solving thing. The ant on the rubber band.
An ant on a rubber band.
If it's, or we can just say like a rubber rope. If it's 1 kilometer long, and the ant's on the one end, trying to reach the opposite end, but the rope or the rubber band is expanding by 1 centimeter per second.
I have seen that. I have seen that problem. Yeah, I've seen a version of that problem. Yes.
Just made me think of that.
That would have to do with like infinite series, which we'll talk about. We can probably address that problem more in chapter 8. Okay, so I want to take this curve between 0 and 1. I want to wrap it around the x-axis and find the surface area. All right? So I know since I'm going around the x-axis, I know that the area of this, surface area, if you want to put SA, whatever, is going to be 2 pi integral of y ds. Now, we get to choose what we want to use for ds. Do we want to use the one that has y prime in it and we'll be integrating with respect to x? Or do we want to use the one that has x prime in it and we'll be integrating with respect to y? With respect to x. And that's because this function is already a function of x, right? And so if we ask for y prime, it's going to be very simple. If we ask for x prime, we're going to have to solve this for x, right? Okay, so I'm going to use the formula that's going to go 2 pi integral a to b. That's the one I'm going to use. This will be y, and then root 1 plus the y prime, that thing, squared dx. So this will become, we need to still, do you see that to do a surface area, you still have to do everything you did for an arc length? Except you have to throw one more thing out in front of the integral. So the work, all the work is still pretty much the same. So here we go. Let's look at y prime. So we have a little chain rule here, don't we? Derivative of root of something is 1 over 2 times the root of that something. Then times the derivative of what's inside the root. What's the derivative of what's inside the root? E to the x. Okay, so that's our derivative. Then we need to square it, don't we? So if I square it, I square the top, I get e to the 2x. Bless you. And then if I square the bottom, ooh, I like squaring the bottom, right? Because that 2 is going to become a 4, and then that root's going to go away, and I'm just going to have 1 plus e to the x. So I'm kind of happy about that. We all good? And then I'm supposed to put 1 plus that somewhere, right? 1 plus that? Let me try that here. 1 plus that derivative, I'll do parentheses, squared, equals, okay, so if I take 1 and I add to it e to the 2x over 4 times 1 plus e to the x, that's the derivative squared right there. I'm adding 1 to it. I'm going to just do common denominator again. So I'm going to take this 1 and rewrite it as this over itself. So we should get the 4 times 1 plus e to the x plus e to the 2x all over 4 times 1 plus e to the x. So that's what I would get if I put them together, right? Now, can I do anything there? Let me see. I can distribute a 4 through here, right? Does that help us, though? Does it? Yeah, I mean, it's 4 plus 4e to the x. Let me do that. So that's going to be 4 plus 4e to the x plus e to the 2x all over 4 times 1 plus e to the x, like that. Does that numerator factor? It does factor. It does factor. It might be easier if you look at it this way, e to the 2x plus 4e to the x plus 4. If you look at it that way, this is like a quadratic. Because of that 2x, that really means like e to the x squared, right? So it's like u squared plus 4u plus 4. So we do a little factoring here. See, I'm just not quite sure where you are with this. What is this? E to the x plus 2 squared all over. We'll just leave this alone. 4, 1 plus e to the x, like that. Okay, so that is the derivative squared plus 1. Yeah? And I'm supposed to take the square root of that, right? But I also have y is out front. Yes? Okay, so this is all going to work out. Let's see what happens. I'm going to start writing the integral now. So this area is 2 pi integral from 0 to 1 of y. Now what's y for us? Square root of 1 plus e to the x times the root of e to the x plus 2, that quantity squared, which is going to be nice when I clean that up, then over 4 times 1 plus e to the x, then dx. Do y'all see what's going to happen here? With that root? Let's see what happens. I'm going to do it without rewriting the whole thing. When I take the root of the top one, the square goes away, right? Yeah. So that goes away. And when I take the root of the bottom one, I take the root of 4, which becomes 2, and I take the root of this, right? Which becomes the root of that, right? So that's what happens when I take the root of, I should have done it here, just take the root of this, and you get that, right? Now, do you see what happens there? See the cancellation? And that kind of saves our lives right there. That really, really helps, doesn't it? Because now I can take that 2 on the denominator, right? And I can just move it out, and it'll kill off the 2 out in front. Right, this 2 and this 2 will kill each other off. So we've got a pi here, we've got integral 0 to 1, and the only thing we have to integrate is e to the x plus 2. And I can do that term by term, right? Antiderivative of e to the x is e to the x. Antiderivative of 2 is 2x, and then we just plug in numbers and we're there, right? So that worked out? Okay, I'm just going to leave that to you now. So if we take that curve between 0 and 1, wrap it around the x-axis, the surface area would be that number, whatever it is.
And that's excluding the, I guess, the circles outside? We're only focusing on the function?
Yeah. So that has nothing to do with the end caps. The end caps, that's what you're talking about, right? Yeah. So in Calculus 3, we would do something like that. We would have an object, that we would look at all the different surfaces, yeah. But we have much more efficient ways of doing it in Cal 3, a much better approach. Okay, let's do another one. How does this seem to you all? Do you miss integration techniques right now, or this is okay? All right, let's try this one. Same instructions. This time x equals 1/3 times the quantity y squared plus 2 raised to the 3 halves. And we're doing this on y between 1 and 2. And we're trying to find the surface area if rotated about the x-axis. I do have some good news. We will not rotate, when it comes to surface areas, we will never rotate anywhere other than x-axis and y-axis. Okay, so you know with volumes, we had these different lines that it could be. We had to look at like outer radius, inner radius, and all that stuff. That with surface area, that won't happen. We're going to stick just to x-axis and y-axis. That's it. Now, could you? Yes, but we're just going to leave that alone. All right? It wouldn't be that difficult to extend the idea, but the book doesn't even do it, so we're not going to do it. All right. So when you look at this, we're going around the x-axis, right? So since we're going around the x-axis, we want to use this formula. And we get to use, for ds, we get to choose, right? Now, we would prefer to use x prime this time, right? Because this is solved for x instead of y. Agree? Yeah. So I would like to go 2 pi integral c to d, which are my restrictions on y, which is given to us, right? And then it's going to be y, and then square root of 1 plus, I'll say x prime squared dy, dy, right? dy. Something is about to happen that I think is kind of weird. We're going to have to put x prime right here, right? And square it and add 1. All that's the same, right? So we're going to do that. When we take derivative of this, our derivative here is going to have y's in it, right? And that's good because we're integrating with respect to y. But out here, y, this right here, in the previous problem, we replaced y with what it was, right? Which was like some stuff with x's in it. But if we're supposed to put y here, and y is our independent variable, then it's just going to stay y. Like we're not going to replace this with anything. It's just going to be y. Okay? Because there's nothing to replace it with because that's what we're integrating with respect to. That make sense? Okay. So this actually works out really nice. This is going to be 2y integral 1 to 2 y and then square root of, and then I'm going to fill this in just a second. So I'm waiting. I'm going to go do my scratch work and come back and fill that in. I guess what I'm trying to get you to see is this. We're wrapping around the x-axis, right? And for the x-axis, the formula has a y here, ds. If we were wrapping around the y-axis, what's the formula? If we were doing y-axis instead, we would have 2 pi integral, it would be x ds, right? So if we chose to use this for ds, this would have to be x, right? If we were going around the y-axis. And then I would replace the x with all of this because I'd be going with respect to y, so I'd need y's in there. So you can get, I hope that makes sense. I don't want to overcomplicate it. We're going to do 2 more examples. We're going to go around the y-axis with 2 other problems, so hopefully it'll become crystal clear at that point. All right, here we go. X prime. All right, so we get to pop this guy out here, right? 3/2 comes out. We just get 1/2. And then it's all of this. We don't touch this. And we subtract 1 from the power, so we get 1/2. And then times the derivative of what's inside, which is 2. Oh, look at how nice they made this for us. 2's cancel, 2.5 cancel. And I get to square that, right? What's the next step? I square it. So when I square that, since these are multiplied, right? That y and that, I just square each one. So when I square the square root, it goes away. And when I square the y, I get y squared. Then I'm supposed to add 1 to that. So 1 plus, and I'm going to go ahead and distribute that through now. Y to the 4th, plus 2y squared. I see it, all right? You see it? They made it just special for us again. That's going to be another trinomial looking, quadratic type looking thing, right? This thing is actually just what squared? Y squared plus 1 squared. And then I'm going to put it under a root, and the root's going to kill it, right? Any questions on what I'm doing here? So this is just 2 pi integral 1 to 2 y times, when I root that squared thing, I just get y squared plus 1 dy. And how would you integrate that? Distribute, right? Multiply this through first, and then just do each one term by term. And you're integrating with respect to y, so everything worked out. Okay? Dot, dot, dot. We good? All right. Now, let's look at 2 more. But this time we're going to go around the y-axis instead. I feel like y'all are getting this. I don't know.
On a test, would you want to
Most likely on the test, I'm going to want, so this is a very good question. Most likely on the test, I'm going to say very specifically for the surface area and arc length problems that you must fully simplify the integrand. In other words, you have to get it to like here, and then you can stop. What you cannot do is write like y square root of 1 plus, and then put that, what was the derivative of that thing again? It was like 1/2 y squared plus 1 to the half times 2y, and then just put like around that squared. Like that you can't do, okay? Because that would be the derivative of x, right? That's the derivative of x squared plus 1. You have not simplified this. So in the instructions, I will say fully simplify the integrand, which means I want you to show me you can get to here. And then I won't ask you to do the rest. Although that would maybe take you another 2 minutes. All right, next one, we're going to do 1 minus x squared. X is between 0 and 1. Surface area about the y-axis this time. So when we go about the y-axis, right, we have to pay attention to that. Our formula is going to change. Our formula now becomes area equals 2 pi integral x ds. And that ds can be anything I want it to be. It can be with respect to x or with respect to y. Which one should I do? The one that has with respect to x, because this one is already solved for y, right? So if I differentiate with respect to x, this is going to be nice and clean. Yes? So we're going to be using y prime in that formula. All right, so for us, we're going to be going 2 pi integral. And since we're going with respect to x, I'm going to use my limits 0 and 1, right? Those are x values. And then I have, according to the formula, x, and then square root of 1 plus, and I'm going to be taking the derivative of y, right, y prime, squared. Y prime squared. So what happens when I take y prime? Let's do that here. Negative 2x, and y prime squared, wow, this one's really clean, is 4x squared. I think I can just plug that in right there right now, right? And I'm integrating with respect to x, because I've chosen to, right? Because it makes the most sense. It's the easiest way to go about this problem. How are you going to integrate that? Trig sub might work. Too hard though. U sub. U sub. What's your U?